I'm very pleased to be here today. I met Mike 30 years ago at the MIT AI lab. He was into physics and I was into AI. And I think I've always had a physics envy. I've always, wanted to understand physics. And I think Mike has always sort of had a reflecting AI interest. They're both some of the most profound questions, I think, of our time. And I think we're both drawn to these profound issues. What's the fundamental nature of reality? And how do we understand the computational processes behind human sentience? So what I'm going to talk about today, I should say that we've been Mike and I have been brainstorming a little bit about AI for the last 5 years. And what I'm going to talk about today is a grand challenge. And I started thinking about this when AlphaZero came out. So AlphaZero is a general learning algorithm. The same code learns to play chess, Go, and shogi all at a superhuman level, simply through self-play. So the grand challenge is, can the same thing be done, or could in principle the same thing be done for mathematics? So the idea here is that mathematics can be thought of as a kind of formal game. If you believe in a formal foundation for mathematics, then there are rules and there are moves. And can the AlphaZero technology be made to do mathematics? And there's a fundamental question here of what is the game of mathematics? What formal foundation do we select to base this on? And how do we formulate the moves and so on? So what is the game? So the real thing I want to focus on throughout this talk is what is the game of mathematics and how can the AlphaZero algorithms be designed to approach this problem? So the first thing I want to do is get a little bit oriented. I'm not the only one thinking about this. People are trying to apply machine learning to formal reasoning. And so far, the success has been fairly modest. So I just want to get oriented. What is approachable in the near term and what things can we think about in the near term? So here are sort of different levels of problem. The first is raising the level of automation in interactive theorem verification. So this is something that's going on and is fairly healthy and active these days. The process of formally verifying, reducing to formal logic, human proofs, even deep human proofs. And that's really what I'm going to focus on today, raising the level of automation in theorem verification. But then Christian Szegedy is really pushing this notion of auto-formalization. So the idea here is you take English, natural language mathematics, and simply translate it into machine-readable form. And there's this potentially strong synergy between the ability to do the reasoning and the ability to formalize informal reasoning, because when there's ambiguity in the formalization, the ability to determine which interpretation works would be based on the ability to actually reason with the formal interpretation. And I find this happens when I read a paper. You've got a couple different interpretations. Some of them work, make sense, and some of them don't. Then we can imagine a completely automated verification system that simply reads natural language papers, or ultimately maybe the MathZero, where the system simply plays with itself and learns to be a mathematician. But I'm going to be focusing on one, raising the level of automation in interactive theorem proving. So just to get oriented again, and to get a feeling for what's happening in this area of theorem verification, just a list of recent results. So in 2013, the Cox system was used to verify the Fayette-Thompson theorem, the odd order theorem in group theory. And that was done by Gunthier. And that was a couple person years of work to put. That's a huge proof. It's like a book length proof. More recently, just in 2019, the lean system was used to verify the independence of the continuum hypothesis. And again, this is viewed as a reasonably long proof, somewhat deep proof. In June of 2021, lean was used to verify a very recent sort of cutting edge theorem. I'm getting an echo. Does someone have another speaker turned on or another microphone? Okay. This was particularly eventful because this is the first time that proof verification was used for current mathematics as opposed to older mathematics. Lean is currently being used to verify the eversion of the sphere. So the point here is this is an active area. The dominant system is lean. This is a descendant of Koch. Importantly, lean is based on dependent type theory. So this is important because we're trying to understand what the game of mathematics is. And part of understanding what the game of mathematics is to pick a formal foundation, because you're going to be, this game is all about doing mathematics, being sure you're right. And to make it a formal game, we need a formal foundation. So here's an outline of what I'm going to talk about. The first thing is I'm going to talk about dependent type theory. Dependent type theory is the foundation for lean. And I want to say a little bit about mathematical logic in general. This is a formal logical system. These days, PhDs in mathematics, many of them, don't have to take a course in formal logic. So mathematicians and physicists think about the objects themselves, right? They're working at a level where they're not thinking about logic, not thinking about formulas. So there's an analogy I want to make here between what happens in chess and Go and what we're thinking about. What we're thinking about here with this grand challenge. So the people who built AlphaZero are not chess players or Go. I mean, some of them are chess players and Go players, but that's not the expertise that is involved in building that algorithm. That is a learning algorithm, and it's general. It learns, it can learn chess or Go or shogi with the same algorithm. So the study of these learning algorithms is different from playing the games. So the idea is that in mathematics, the study of the foundations of mathematics, meta-mathematics or logic, is just a different subject. It's from doing the mathematics. And so what I want to, if you're a physicist, I'm sort of shifting gears here, and this is not going to be doing mathematics. It's going to be studying logic. So I'm going to start by sort of formally introducing dependent type theory. And then we're going to take a close look at AlphaZero. And then I'm going to talk about innovations in verification technology that I'm going to suggest may change the game. The question here is, what is the game? So here's an outline. So dependent type theory. Why type theory? So the standard foundation for mathematics is set theory, Zemelo-Fraenkel set theory with choice, ZFC. What's different about type theory and what does type theory provide? Now, if you picked up a book on type theory and started reading about it, there would be a lot of stuff that I can consider to be sort of obfuscation. It would talk about propositions as types and constructivism. But the real essence that I want to focus on is types as providing abstraction barriers. So in type theory, independent type theory, what we're going to get is types. And these types are going to include the structure types of Bourbaki's notion of structure. And what types provide is a kind of abstract interface. And this abstract interface supports a notion of equivalence between two objects. In computer programming, you can have two implementations of the same class that produce identical behavior. In mathematics, you can have two representations of groups that are different representations, but are isomorphic as groups. So these types provide an abstraction barrier, which is associated with the notion of equivalence. And that notion of equivalence is precisely the standard notion of isomorphism on structures, or the standard mathematical notion of isomorphism. And for me, that is the essence of why we move from set theory to type theory. It's these abstraction barriers where the equivalence is precisely the standard mathematical notion of isomorphism. And I've said this slide already. Set theory does not come with, set theory is like a machine language, right? It's untyped, but type theory is providing these abstract interfaces. Okay, now I'm going to try to do a very gentle introduction to dependent type theory. So the idea here is I'm going to treat dependent type theory as just a formal notation as you would treat any other formal notation in mathematics. So in mathematics, when you introduce notation, you simply say, well, here's the expression I'm introducing, and here's what it means. And then you reason about it in any way that's correct. You use that notation in any way that's correct for its meaning. So I'm going to introduce dependent type theory simply by saying what the expressions of it are. It's a formal language. It has formal expressions like a programming language. What are the expressions and what do they mean? I'm not going to talk about inference rules. You're free to use any inference rules that work for those meanings. So we're going to start by saying there are these type constants, set and bool, and we can introduce typed variables. So I can say S is a set, or F is a function from S to S. And then in type theory, we're going to have types, where set is a type, but we're also going to have function types like S arrow S. And this is dependent type theory. So we have a dependent function type, which is historically written with this pi constructor. So if I say pi x of type tau, and this is a type, this is the type of all functions whose domain is the type tau, and such that if I apply f to something in that domain, I get something of a type that can depend on x. So if I had, so for example, I can define a function from a number to a number greater than that number, where the idea of being a number greater it would be a type, a dependent type. We also have pair types. This is a dependent pair type. This is the type of pairs, x, y, such that x is in tau and y is in a type that depends on x. So x might be a set and y might be a function from that set to that set. So the type, if we go back here, if I have a pair of a set and a function from that type to that type, the type of the second component of the pair depends on the value of the first component, and that's what makes it dependent. We also have restriction types. I can take the type of elements of a type tau satisfying some Boolean formula. And finally, this is the last slide, we're done. This is supposed to be a very quick, gentle introduction. We have function expressions. If I write lambda x of type tau, e of x, that's the function that maps x of type tau to the meaning of this expression. I can write a pair of two values. I can take the first component of the pair, the second component of the pair. I can write Boolean formulas, maybe a predicate, a function from some type to bool, or an equation between two elements, or universally quantified formula, or standard Boolean expressions. So that was very quick, but that is dependent type theory. So here's an example. A group, you can define a group to be a pair of a set plus a function that maps two elements of the set to a set, the group operation. And then I can write axioms that has to satisfy, such that there exists an identity element and an inverse operation, plus the standard group axioms over that. Okay, we have one more element of dependent type theory. and that is the notion of a sequent. So a sequent is just a kind of implication. So if I can say gamma implies something, some data, and here gamma is going to be a set of variable declarations. I'm going to just define one of our fundamental things in our language was to have a typed variable. So gamma is going to declare variables. It's also going to make Boolean assumptions. And then this will either be a type assertion that some term is in some type, or it'll be some Boolean formula. And this just means that this is true or valid if this is true under any variable interpretation satisfying the declarations and assumptions here. So again, it's quite simple. And then what's really important, so I think the fundamental thing that type theory provides that you don't get in set theory is this substitution principle, this equivalence principle. You get an equivalence notion associated with every type in this system. And this is, now a very rich system. You can talk about, it's open domain. You can talk about anything in mathematics. If you think about group theory, the language in which group theory is expressed is not the language of groups. It's not just the terms. It's all kinds of operations on groups and representations of groups. So mathematics in general is very open domain. Concepts interact across all of the concepts of mathematics. And what this substitution principle says is that even in this completely open domain discussion, open domain language where concepts are interacting, if I have any context, so suppose this was the type group, I've declared X to be a group. If I have any context that's well typed, that's well formed for accepting groups, and that might be some expression that has a type tau, then if I have two isomorphic groups, two things that are equivalent at this type, then I can substitute them into this context and they'll be equivalent at type tau. So this is a very general substitution principle for isomorphism, and it relies both on the abstraction barrier associated with group and on the well-formedness of the context into which I'm doing that substitution. And this is really central to mathematics, I think, and is really central to the aspects of mathematics that are central to physics. So symmetry and canonicality. So symmetry is just an automorphism. It's just an isomorphism of something with itself. And we know, just trivially, everybody knows that there's no canonical point on a geometric circle, because if any selection of a point on a geometric circle breaks the rotational symmetry of the circle. And if you go back to Eilenberg and MacLean in the 1940s, when they introduced category theory, their fundamental example was that there's no canonical isomorphism between a vector space and its dual, that's not free of choice. And that's exactly the same phenomenon. Any choice of an isomorphism breaks a symmetry of the vector space. So the point here is that this phenomenon of symmetry and canonicality arises naturally in this very simple notion of type that I just showed you. So one of my contentions with this community is that there's a lot of dogma involved in this community, which I think is completely unnecessary. This notion of isomorphism and symmetry just comes out naturally, and you can treat it independent of category theory. You don't need any constructivist philosophy. You don't need propositions as types. You don't need esoteric interpretations of the type system like homotopy type theory. The set model, the semantics I just defined, is perfectly good. And it really captures what you want to capture, which is this abstraction barrier and equivalence principle. Okay, are there any questions that I'm about to transition to part 2? Okay, close look at alpha 0. So alpha 0, I do believe, is an important general learning algorithm. As I said, it learns chess, shogi, and go. And people who learn one of those games that are not necessarily able to play the others. So it's doing something very general. But I want to put it into a little bit of context here. So it is looking at games, right? Adversarial games. The adversarial nature may not be very important. You can think of it as a general reinforcement learning algorithm. It doesn't have to be adversarial. But I just want to point out that this mathematics game arises naturally in, for example, the lean verification system. So lean is a backward chaining system based on tactics. So a tactic is something that takes a goal, and a goal is going to be a sequent in dependent type theory. We want to prove that that sequence is true, that implication holds. And a tactic is something that takes a goal and decomposes it into sub-goals, and at the same time provides a proof that the sub-goals establish the goal. So it's a backward chaining system. And this backward chaining system generates an and/or search tree, right? At any goal you're trying to prove, you have a choice of what tactic to pick. That's an or choice. Any tactic that works succeeds. That tactic will generate a set of sub-goals. That's an and choice. To make that path succeed, you have to satisfy all of the sub-goals. So you get this and/or tree, which is a kind of game. And the idea is we could maybe apply the AlphaZero game learning algorithm. So now, again, a little more background. I want to mention computer chess. So the first chess algorithm, the first min-max search algorithm, was proposed by Claude Shannon in 1949. It was refined by various people with this notion of alpha-beta pruning circa 1960. And alpha-beta pruning remained the backbone of all chess programs until AlphaGo in 2015, where things got radically different. And it was shocking that alpha-beta could be dropped and you would still get a superhuman chess program. But this notion of min-max searching all the positions in the game and actually constructing a proof that this is a winning position, could not be applied to Go. The branching factor in Go is just too large. So a different approach, AlphaZero is a different approach. And what I'm going to do is AlphaZero has many components. And I'm going to sort of go through the components, where they come from historically, and then put them together in AlphaZero. So I'm going to start with the notion of the bandit problem. So in a game, you have to choose a move. And you can define a very abstract version of choice where you've got a bunch of choices. For each choice, there's some stochastic process that happens when I make that choice. And the question is, which choice is best? So in a bandit problem, you're faced with a set of choices. I can try each one, and each time I try each one, I get some result. And I can try to figure out which choice has the best average result. And this is based on the metaphor is you walk into a casino and you have to select a slot machine. Each slot machine has a payout probability. You want to experiment, try different slots, and find the machine with the best payout. So it's called a bandit problem. But it can be applied to any decision, right? You have to make a decision and you have a reward based on that decision. So there's this algorithm for this problem that was developed in 1985 called the upper confidence bound algorithm. And this is a very well-known and well-studied algorithm. The basic idea is if I'm picking a slot machine, I can, as I do it a bunch of times, I'm getting a bunch of payouts, and there is some expected payout, and I can take the empirical mean over those draws as an estimate of its payout, but that empirical mean has a confidence interval, roughly 2 sigma. So you take that confidence interval of 2 sigma and you look at the upper bound. That's the best payout this machine is likely to have. And you always pull the arm where the upper bound on the confidence interval is maximum, right? And that's called the upper confidence bound algorithm for making a choice. And this is going to play a role in AlphaZero. Monte Carlo tree search. So this was the first major advance in Go. So Monte Carlo tree search is based on taking a Go position, and you take some fast, very fast algorithm for deciding what move to make, maybe even just a random move. And you play that very fast policy for picking moves out to the end of the game. You just do what's called a rollout. You play the game out very quickly to the end, just picking a choice for each player, one choice for each player. And you look at who won. And then you do that again and again. You get a bunch of these rollouts, and you measure how many times with each player won, and you use that as an estimate of the value of this position. Who's ahead, who wins more under a random rollout. And that actually worked somewhat surprisingly to some extent in Go. It was the first major advance in Go. So the next thing I want to talk about is the upper confidence tree. This is where the Monte Carlo tree search and the upper confidence bound algorithm are put together. So the idea here is that at a given position, you've got a choice of moves. And what you do is you go over the moves you have and do random rollouts from each of those moves. And then at each position, you use the upper confidence bound algorithm to select what move to use. And you actually do that as you're playing the game. As you're getting more statistics about each move, the upper confidence bounds are changing, and you develop a stochastic policy for picking a move. In principle, it should always pick the move with the highest upper confidence bound, but you can also make that somewhat stochastic. But anyway, what you do is you're using the upper confidence bound algorithm at each move, at each choice in the tree. And you can do that recursively when you do a rollout. You can recursively be using upper confidence bounds as you do the rollout. Okay, a final component of AlphaZero is bootstrapping tree search. So this was first formulated in the setting of min-max tree search, like chess. So the idea is I've got some parameter vector, phi, and I've got a static board evaluator. So think chess. A static board evaluator is going to take a position and say who's ahead and by how much. And what we want to do is tune the parameters. So this might be something as simple as tuning various features of the board, like the piece count weights or other features of the board, passed pawns. And I want to tune this parameter to be as accurate as possible. Well, what I can do is have a bunch of chess positions, run the min-max search algorithm, and then train and then select the parameters to try to predict the result of the search. So you're bootstrapping the search. The idea is that the search is giving you a more accurate value than the static board evaluator. Train the static board evaluator to match the search. So that's, and all of these things are going to get put together in AlphaZero. So the major innovation of AlphaZero, once you have all these components already, is to replace the static board evaluator and the whatever selecting a move to try from a position with deep neural networks. So we're going to have what's called a policy network and a value network. So in AlphaZero, these are convolutional neural networks that look at the board position. This is an architecture that came out of vision, right? It's the same architecture that started the deep revolution in 2012 with AlexNet winning the ImageNet competition by a large margin. It's the same style of algorithm. This is a ResNet, which is a more advanced convolutional neural network, well established by 2015. So the policy network takes a board position and constructs a probability distribution over the move to make. So this is a stochastic policy. A policy is something that takes a position and selects an action, coming out of the reinforcement learning literature. But what we're going to make it is we're going to make this a stochastic policy. So there's a probability distribution over each move. So we take a position, and at each move is also in Go is just a position on the board. So it's assigning a probability to the various next moves. The value network takes a position and says who's ahead and by how much in that position. And in AlphaZero, what worked best was to use one convolutional neural network to do the policy. and then put a different head on that same neural network to produce the value. So now I'm just going to define the algorithm. It's basically just putting all these things together. So, so we're going to do upper confidence tree with policy and value networks. And the way this works is we're going to replace the rollouts. In AlphaZero, you replace the rollouts with what's called a simulation. So you're going to grow a search tree like in chess, but it's going to be a very sparse tree. You're not really going to expand all the children of any given node. And a simulation is going to be a path from the root position down to some leaf in that tree. And what's going to happen is that every node is going to maintain statistics that are keeping track of upper confidence bounds for all of its moves, for all of the moves from that node. And a simulation is going to be generated by running the upper confidence bound algorithm to predict, to select moves as we descend in the tree. So the upper confidence bound algorithm is being used to select moves. We're going to go to a leaf, and we get to a leaf, we're going to process that leaf. So what happens is the leaves of this tree are unprocessed. And what that means is the neural network has not yet been run at those leaves. So what we're going to do is we're going to go down to a leaf. We're going to process the leaf, meaning we're going to run the neural networks at that leaf. When you run the neural networks at that leaf, the policy network assigns a probability to each possible move. So when you process the leaf, you get new leaves, which are all the leaves are unprocessed. You get new leaves, and each new leaf is going to have its upper confidence bound information initialized based on the probability that the policy network used in assigning that leaf. And then the value network, when you process a leaf, we also get a value network value for that leaf. You take that value and you walk it back up the tree to update the upper confidence bound statistics. And that's AlphaZero. The way it's trained is that's the AlphaZero tree growth algorithm. Now we have to say, how do we train the parameters of those networks? So the parameters of those networks are trained by bootstrapping the tree search. So when you do a full tree search, when you completed the tree search, there's an upper confidence bound policy at the root position based on the upper confidence bounds. And they use a stochastic policy everywhere. Everything's stochastic. So it's not just picking the best upper confidence bound. What you do is you train your policy network to predict the final policy of the tree search, right? The final tree search has a policy. You try to predict that policy with the policy network. You also try to predict who won the game from that position with the value network. When I say try to predict, you're updating the parameters to try to improve those predictions. Okay, so this was chess and shogi. How does this relate to theorem proving? So in theorem proving, in say lean theorem proving, we're running a tactic, something that's selecting tactics. And a tactic is something that takes a goal and gives you a set of sub goals. So we've got we've got a choice of a tactic and a choice of sub goals. So we get this and/or search tree. And so we can try, here's the point I wanted to make. The tactic itself is written as some kind of character string. And that character string, to generate a probability distribution over character strings, we can use a language model. So there is ongoing work in trying to use language models to select tactics in proof verification. So here's a list of recent attempts. In my opinion, the results have been quite modest. So that's where this stands. So finally, part 3, changing the game. So this is what I'm most interested in as a research area. So lean is a backward chaining system. And every time you apply a tactic, you have to construct this proof that the sub-goals imply the goal. There's another approach to automated reasoning based on something called SAT modulo theories, or SMT. And there's a system called Z3. And Z3 has been described as magical in the level of automation that it achieves. What I'm going to try to do is just give a high-level intuition for how Z3, or what is this magic? And a natural question is, can we shift the underlying mechanisms in our proof verification systems in a way that changes the game that we're going to pass to the AlphaZero algorithm? In any case, the real question is, does SMT technology improve proof verification or formal reasoning? So this is a flow chart, sort of a visualization of the Z3 architecture. So the basic idea in SAT modulo theory is that you're taking SAT solvers and augmenting them with other kinds of inferential mechanisms. So a SAT solver just takes a Boolean satisfiability problem and searches for a truth assignment satisfying Boolean constraints, the Boolean satisfiability problem. In an SMT solver, you also have this congruence closure algorithm that propagates equality, something that instantiates lemmas. And these are all connected to this, passes information back and forth with the SAT solver. You also have theory solvers like linear arithmetic. If we're going to do this for type theory, we want these theory solvers to include, to really be more like lemma libraries, your background knowledge. So let me break this down, make it a little, view it at a little bit higher level. So a SAT solver, SAT, Boolean satisfiability, is the primordial NP hard problem. So SAT solving is NP hard. That's supposed to make it intractable. Modern SAT solvers can solve hundreds of thousands of Boolean variables. So this intractability has not really stopped the construction of SAT solvers. An very important property of SAT solvers is unit propagation. If the SAT solver can determine that there's a particular value that's forced for a particular variable, it'll adopt that value. So it's got an inference, a forward chaining inference process built into it. And I'm going to call that, in general, propagation, forward chaining derivation of more information. Congruence closure is this very fast algorithm for propagating equalities. It computes all the consequences of equality, all the equivalence relation consequences and substitution consequences, the congruence consequences in an n log n algorithm. An SMT solver also has an E-matcher, which is basically something that's finding instances of lemmas. So if you've got some statement that you want to instantiate, and then there's theory-specific propagation, like your linear arithmetic solver is going to be determining the value, the truth of some inequality, and propagating information through the theory-specific mechanisms. The point here is that all of these components are involved in propagation. They're passing information among themselves. And this propagation process is run to completion. The propagation algorithms are designed such that they always terminate in a feasible amount of time. And all of these components are talking to each other in this propagation process. So this is just a slide saying what I just said. The point here is that you've got a forward chaining closure that involves many different sources of information. You've got the congruence closure, you've got the Boolean unit propagation, E-matching. And this is very different from backward chaining. When you backward chain, you might employ some tactic that might have some knowledge about algebra or arithmetic. But that choice of that tactic is very different from allowing all of your sources of information to talk to each other in a forward chaining manner until you get some kind of closure. So this is a very different way to think about what's happening under the hood in the verification process. And propagation is very closely related to the algorithmic concept of dynamic programming, right? In dynamic programming, like in Dijkstra's shortest path, you want to know, what's the shortest path between two nodes in a graph. And there can be exponentially many different shortest paths, but the dynamic programming algorithm simply enumerates the shortest paths in order of length, and ignores the fact that, and that's like a propagation algorithm. It's ignoring which, it doesn't really care about which path there is as it propagates the information. And another point about propagation, a propagation-based, forward chaining-based inference system, is that it better supports declarative proofs. So what I mean by a declarative proof is that if you think of a proof as a tree, you're proving you're making case analyses and proving various parts. If you think of that as a tree, in a declarative proof, you do not mention any tactics or any, you don't even need to mention any hints about what lemmas to use. You simply say what your goals are, what your variables are, what your goals are, what your case suppositions are, and what statements you find to be obvious. And here's a declarative proof written in ONTIC, which is a system I developed at MIT 25 years ago, and it was later refined by Bob Given at Purdue. So this is a proof Bob Given did of the Schroeder-Bernstein theorem. So this is very close to the foundation of mathematics. The Schroeder-Bernstein theorem says that if you've got two sets, any sets, and I've got an injection of A into B and an injection of B into A, if both injections exist, then a bijection exists. So it's saying basically that cardinalities are ordered in a natural way by injections. This proof is, I'm not going to go through this proof, of course, but I just want to point out that there is no reference to tactics in this proof. It's completely declarative. There is not even any reference to what lemma to use. This is purely just consider a variable of this type. We're trying to show, or a system of variables, we're trying to show this statement. Suppose this statement is true, or introduce this object and see that this is true. And that's the only structure this proof has. And this proof, with only that structure and no hints, replaces about 5 pages of Calc code. I want to be a little careful about that. I don't want to make any general claims. We have not done a systematic comparison with Calc, but this is technology from a long time ago. It just never, I think for PR reasons, we never really got much attention. But I just want to point out that this notion of a declarative proof defines a very different notion of game that we could be playing, that we could be applying the AlphaZero algorithm to. Okay, so conclusions. Type theory in AlphaZero. So I've argued that if you're going to address this grand challenge of automated development of mathematics, you really want to be working in dependent type theory. Dependent type theory is a much better model of human mathematics than set theory, for reasons that are, I think, obfuscated in the type theory community. AlphaZero is, I think, a really legitimate and appropriate model for what one might use in this grand challenge. It's incredibly general, based on very general principles that are a combination of principles that are quite old. And the final conclusion is just this idea of SAT modulo type theory. The idea is that we want a type theory verification system that's based on propagation algorithms in the style of SMT solvers, and that a change in the fundamental, change in the way we think about what a proof tree is will change the game, may change the game in this program or project. So I'm happy to take questions.
Questions for David?
Yeah, David, thanks. That was great. And it was very complimentary to the other talks, which were kind of not there was questions, how do these things work inside? And I think you gave more of a sense of what's going on inside. I think this SMT work is very interesting, but I'm not sure it's so different than, it could be combined with Koch and Wien and the others, because you could just say there is some powerful tactic which does the sequence of forward chaining steps, and in fact there's CC and synth and so forth. There are tactics that do a lot of that stuff, and that could just be the default option. And then you still have a tree, because in a declarative proof you have to still choose your next declaration, goal to try to approach, and that's the information of the proof. And when you generate a proof, you still have to generate those. Your procedure is not in itself solving that problem, right?
Yeah, that's a good comment, and that's right. One way to think about it is people talk about the hammer tactic. And Larry Paulson, who pushes this notion of declarative proof, will say, well, we'll only have one tactic, we'll call it hammer. So I guess it's sort of a change in, so it is true that whatever I do with this SMT thing, I could call it hammer and just always say hammer. The idea, though, is that you change, is that if you have a strong enough hammer, it sort of changes it changes the set of proofs that the system will accept. And by changing the set of proofs that the system will accept, that you're sort of shifting the game. So it's really no different from saying just how do we improve the level of automation in these systems? But I do think there's a little bit of a mind shift, a shift in perspective, if you start saying, well, really what we want to do is just always use hammer. It makes the choice shifts from selecting a proof technique, an algorithm to generate subgoals, to an algorithm that's selecting what case to make or what goal to assert. So I do think there's a shift in perspective, even though I could build this into Lean as a hammer tactic.
Well, I guess a potential difference. Hammer also, does some premise selection, and then it runs all of its, logic and proving. And so did you imagine your basic forward changing step is operating on the whole database of lemmas and selecting what it needs, or
That is what I'm imagining.
Okay.
Right. Because when people get sufficiently familiar with an area, they just talk about what's true, and they stop saying exactly what lemmas. Sometimes you say this follows by, and it helps. But there's a lot of stuff being used just subconsciously. So I'm very interested in modeling, how you take a bunch of stuff and get it built into the sort of notion of obvious that the machine is implementing.
So, I have a question. So, in your previous page, you made reference to Wigner's essay about unreasonable effectiveness, and you were saying that you think type theory somehow helps helps that unreasonable effectiveness. Could you expand on what you meant?
Yeah, in the unreasonable effectiveness of mathematics, we're referring to mathematics, right? What is math? This raises the question for me of if we want to understand, this is very philosophical, but if we want to understand where that power comes from, physics has put a lot of weight on symmetry. Symmetry is not there in set theory, right? We're not saying the unreasonable effectiveness of set theory. I don't believe set theory is unreasonably effective. What's unreasonably effective is the structure of mathematics that arises when we put abstraction barriers on things, right? When we understand that an object has a symmetry group, or the notion of isomorphism. So I think it's just a matter of when we say the unreasonable effectiveness of mathematics, what do we mean by mathematics? Do we mean ZFC set theory, or do we mean what mathematicians do, which is modeled much better, I think, by dependent type theory. Dependent type theory is kind of an unreasonably accurate model of mathematical thought, in my opinion. I don't know. Did that?
Interesting. Definitely interesting to think about. Yeah. Any more questions? I'd like to echo Mike's thanks for actually opening up the box and telling us about what was inside it, because I think for many of the physicists this morning, it was really interesting what everybody said, but how does this even work was a question. So thanks a lot.
Sure. It was great.